Okay, students, now this is a compensator which is 100% clear because it produces the finite poles and finite zeros. Now I want to identify which type of a compensator it is. Is it right or not? So, what is the transfer function of this compensator? V naught of S by Vi of S, which is equal to 1 plus tau S by 1 plus alpha tau S. Now this is the time constant and corner frequency is inversely proportional. You know that. Time constant and corner frequency is inversely proportional. Omega c equal to 1 by tau. Now this is omega c equal to 1 by alpha tau. Now this is omega c, which is equal to 1 by tau. Now this is the corner frequency and time constant which is inversely proportional. So then this compensator is a lead compensator or not, we want to identify, right? So you have already a frequency response plot called as Bode plot, polar plot, Nyquist plot. But Bode plot will use the phase characteristics directly. So phase versus frequency response of plot is already available. So you draw the phase versus frequency response, which is nothing but a Bode phase plot. For this particular compensator, you can easily identify whether it is a lead compensator or not. Is it right or not? So I will try to draw the Bode plot. So while Bode plot, if you want to draw, first convert it into time constant form. Already this is in the time constant form, k into 1 plus st1 by s power n into 1 plus sta and so on like this. Okay. So if you compare these two and identify the system gain, what is the system gain k? System gain k equal to 1, and what is the starting magnitude in terms of dB? The starting magnitude in terms of dB is 20 log k base 10, k equal to 1, which is nothing but 0 dB. Therefore, the starting slope which is equal to, is there any poles at origin? No, no pole at origin, no zero at origin. Therefore, the starting slope is 0 dB per dk. Okay. Now, this is the information which we can identify from the transfer function. And one more thing also you can identify n number of times I am saying. Let us take this is -1. What is the time constant? Time constant is 1 second. Let us take this is -2. What is the time constant? 1 by 2, 0.5 second. What is the relation between time constant and corner frequency? Always inversely proportional. Now, who is nearer to the origin? Listen. Who is nearer to the origin? That fellow is having highest time constant. Who is nearer to the origin? That fellow is having highest time constant. When highest time constant means least frequency. Who is nearer to the origin is having highest time constant, is having least frequency. Who is away from the origin? See, who is away from the origin is having least time constant. When time constant is least, corner frequency is high. This is the highest corner frequency. So how you can remember? Who is nearer to the origin is the least corner frequency. Who is away from the origin is the highest corner frequency. Because time constant is more, frequency is less. Time constant is less, frequency is more. So who is nearer and who is away in our compensator? Because just now we finished the post zero sequence of lead compensator. This is 0, this is pole. Is it right or not? So 0 is nearer, therefore this is the least corner frequency because this is the highest time constant. So pole is far away, this is the least time constant and highest corner frequency. This is the highest, this is the least. So what is omega c1? Omega c1, which is nothing but 1 by tau omega c1, which is equal to 1 by tau omega c2, which is equal to 1 by alpha tau. These are the corner frequencies and this is the ascending order. Why? Because while we want to draw the Bode plot, now first we want to convert it the time constant form and write the corner frequencies in the ascending order. Okay. So this is the corner frequencies in the ascending order. Now first what Bode plot. First we will draw the Bode magnitude plot. What is the Bode magnitude plot? Magnitude in terms of dB. V naught of S, Vi of S. Magnitude, or this is nothing but a gain in terms of dBs versus frequency. Frequencies. Write the corner frequencies in the ascending order. Write the corner frequencies. First corner frequency belongs to 0. Second corner frequency belongs to pole. This is omega C1. This is omega C2. Now, starting magnitude is 0 dB. Starting magnitude means 0 dB here. Starting slope is 0 dB per decade. Starting slope is 0 dB per decade. This is 0 dB and this is 0 dB per decade. Now, this 0 dB per decade is up to the first corner frequency. First corner frequency belongs to one finite zero. One finite zero produces a slope of plus 20 plus 0. So this is plus 20 dB per decade. Plus 20 dB per decade. This is up to the second corner frequency. Now what is the second corner frequency? The second corner frequency belongs to one finite pole. One finite pole produces a slope of minus 20 plus 20. 0 dB per decade. Note down this. Now this is the Bode magnitude plot. So it is very easy to draw the Bode phase plot once the magnitude plot is available with us. Now phase angle in terms of degrees. Now this is 0 dB per decade, which means this is 0 degrees. Now this is 0 dB per decade, this is 0 degrees. So this is plus 20 dB per decade, this is plus 90 degrees. Now this is 0 dB per decade, this is 0 degrees. Okay. So, but this, your phase is completely depends upon the frequency, because this is finite poles and finite zeros. Therefore, you know how to draw the Bode phase plot. Now this phase is completely depends upon the frequency. See here. Now this is the leading phase or not? Yes, this is the positive phase. This is the leading phase. Therefore, this compensator is nothing but a lead compensator. this compensator is nothing but a lead compensator. This compensator is nothing but a lead compensator. Now this is the lead compensator. Now see here. This is the frequency. So at this particular frequency, we can get this phase, maximum phase. At this particular frequency, we can get the maximum phase. Let us assume this frequency is omega m. We have one shortcut method. You can find directly that frequency. Omega m is the frequency at which the maximum phase will occur. Okay. Omega m is the frequency at which the maximum phase will occur. Now, what is omega c1? Omega m is the frequency at which the maximum phase will occur. That omega m is the geometrical progression of two corner frequencies omega c1, omega c2, which is equal to 1 by tau and 1 by alpha tau, which is equal to 1 by tau into root alpha radians per second, because always these characteristics are depends upon the compensator parameters, and this is a maximum phase lead. The maximum phase value, which is nothing but sine inverse. Now this is alpha, then this alpha here is less than 1, therefore this is nothing but 1 minus alpha by 1 plus alpha, because alpha is less than 1. No doubt. So this is the maximum phase at which you can get this maximum phase at this particular frequency is a geometrical progression of two current frequency, where this, if you observe these characteristics, is completely depends upon the compensator parameters. Okay, so where here everything will be same, where alpha is R2 by R1 plus R2, which is less than 1, where tau is R1 C1. So this is very clear, then this is nothing but a lead compensator. Not only that, you can also observe here, this is the gain versus frequency characteristics. This is the gain versus frequency characteristics of a filter. See here, this is pass band, this is the pass band, and this is stop band. This is pass band, this is stop band. Now as the frequency is greater than this, cutoff frequency is pass band, the frequency is less than this cutoff frequency is stop band. So this is a pass band, the frequency is greater than this cutoff frequency is pass band, the frequency is less than this cutoff frequency is stop band. Now see here, this is the gain versus frequency characteristics of a which filter? High pass filter, right? So now similar to here, this is the output you are taking. This is the output. This output is across resistor. This output is across a resistor, and which system? First order system. For a first order system, and output is across a resistor, it will act as a differentiator. Am I right? Not. Differentiator is nothing but a high pass. Now similar here, the frequency is less than this is 0, the frequency is greater than this is plus 20. Okay, the frequency is less than this is 0, the frequency is greater than this is plus 20. So this is the gain versus frequency characteristics. This is the gain versus frequency characteristics of a high pass filter. This is the gain versus frequency characteristics of a high pass filter. Now this is the high pass filter, and similar to your gain versus frequency characteristics of which compensator? This is Lead compensator. So this lead compensator is similar to a high pass filter. Therefore, the lead compensator will act as a high pass filter. Lead compensator will act as a high pass filter. So if it is a high pass filter, what is the pole zero sequence? If it is a high pass filter, now the pole zero sequence is, this is the pole zero sequence of high pass filter. Now most of the times in the GATE examination, now he is giving some circuits, okay. Now he is giving some electrical circuit and he is asking to find which type of filter it is. So simplify those circuits like this and locate the poles and zeros in S-plane. Those poles and zeros location is like this. First one is 0, next one is pole. First one is 0, next one is pole. Then that particular circuit will act as a high pass filter. Okay, note down this. Okay, so clear or not? This is the compensator because it produces the poles and zeros, and this is the lead compensator because it produces the leading phase, and this is the phase and this is the frequency where you can get the omega m is the frequency, not maximum. M means frequency. At this particular frequency, phase is maximum. Okay, omega m is the frequency where we can get the maximum phase. Okay, so we will see the effect of lead compensator. What is the effect of this lead compensator? So before we will see the effect, I just give a few points. Okay, you note down that this is the noise power. Noise power is equal to K Tn B. K is Boltzmann constant. Tn is noise temperature or also called as thermal noise. B is bandwidth. Okay, K is Boltzmann constant, Tn is noise temperature, B is bandwidth. Okay, so K is constant at a particular temperature. This is also constant. Therefore, noise power is directly proportional to bandwidth. What is the meaning of that? As B increases, this is directly proportional. As B increases, noise power is also increases. As bandwidth is decreases, noise power is also decreases. Directly proportional. Next, signal to noise ratio. Signal power to noise power. Signal power to the noise power. The signal to noise ratio is as high as possible such that effect of noise is less. Is it right or not? If this is very, very high, signal to noise ratio is very, very, very high, then this effect is very, very less. Okay, so effect of noise is very, very less. So there the effect of noise is less, that particular systems will have more signal to noise ratios. Okay, means for a best signal to noise ratio is far greater than 1 for best systems. So when signal to noise ratio is far greater than 1, effect of noise is less. When the signal to noise ratio is less, as low as possible, then the effect of noise is as high as possible. Noise effect is dominating, characteristics are disturbed. Okay, these two are the important parameters while we are discussing the effect of Lead compensator. Okay, what should be the effect of a lead compensator? We will see now. Now I'll see, I will explain one by one. Okay, effect of lead compensator. Okay, now see here, first of all, this is a compensator. Lead compensator produces finite zero and a finite pole in the left hand side of S-plane. Lead compensator produces a finite zero and a finite pole in the left hand side of S-plane. Now see here, the lead compensator produces a finite pole and a finite zero in the left hand side of S-plane. And here one more parameter also you can easily identify. Now these are the first point, this is the second point, and this is the third point. The third point is nothing but bandwidth and rise time is always inversely proportional. Rise time, you know what is the rise time definition and everything. Okay, so bandwidth and rise time is always inversely proportional. Now see here, lead compensator is a high pass. Lead compensator is a high pass means high frequency means bandwidth is more. Is it right or not? Lead compensator is high pass filter means high frequencies means bandwidth is more. When bandwidth is more, bandwidth is inversely proportional to rise time. When bandwidth is more, rise time is decreases. When rise time is decreases, settling time is also decreases. System becomes faster. So this point I can explain with the help of one diagram here. So first you note down these 3 points which are important. Noise power is directly proportional to bandwidth. Signal to noise ratio is very high for a good systems, and bandwidth and rise time is inversely proportional to each other. Now, I just take a reference response as the underdamped response. Now, this is the time taken by the response. This is the time taken by the response to rise from 0 to 100%. The time taken by the response to rise from 0 to 100% is called as rise time. Is called as rise time. Is it right or not? The time taken by the response to rise from 0 to 100% is called as rise time. 0 to 100% is called as rise time. Now what happened? Now this is a high pass filter, therefore high frequencies, therefore bandwidth is less, so bandwidth is more. When bandwidth is more, rise time is decreases. Now what happened? Now the rise time is decreases. The time taken by the response to rise from 0 to 100% is now decreased. Now what happened now? The time the time taken by the response to rise from 0 to 100% is now decreased. Now rise time is decreased. Previously this much and this is the rise time. Now tell me, what is previously the settling time? The time taken by the response to reach its final value is called as settling time. Previously this is settling time of 100 seconds. Now what happened? The time taken by the response to rise from 0 to 100% is rise time, and to reach the final value is called as settling time. Now this is the final value. Okay, let us take some 80 seconds. 5 examples. Okay, all these are 5 examples. Now what happened now? Now this is a high pass filter. Bandwidth is increases, high frequencies. When bandwidth is increases, rise time is decreases. When rise time is decreases, settling time is also decreases. When settling time is decreases, it will take 100 seconds for reach to final value. It will take 80 seconds. Now system becomes faster, and by this we can conclude that the lead compensator is to improve the transient behavior. This is the actual response. Lead compensator is improve the transient state analysis. Lead compensator is improve the transient state analysis. Clear or not? It improves the transient state behavior. It improves the actual response. Now see here. We know that the noise power is proportional to the bandwidth, but here bandwidth is more, noise power is more. So what happens when noise power is more? Signal to noise ratio. Noise power is more, noise power is more, noise power is more, noise power is more. When noise power is increases, denominator is increases, then the signal to noise ratio is, therefore signal to noise ratio is less. When signal to noise ratio is less, what happens? When signal to noise ratio is less, effect of noise is very high. And noise can easily enter into the system. Noise can easily enter into the system. Understand not? So effect of noise is very high and noise can easily enter into the system. Now see here, now the next point, the lead compensator is similar to, now see here, this is similar to a PD controller or not? What is a PD controller? See here, in the proportional derivative controller, the PD controller. Now PD controller means proportional plus derivative, Kp plus Kd into S, which means that this is a finite zero, one finite zero. Now here is also, what is the first one? First one is important because this is the dominant one, finite zero, because zero means rising, high pass, that is also high pass. Therefore lead compensator is similar to PD controller, because in PD controller also a finite zero is available. Understand or not? And One problem here, see here you can say that noise can easily enter into the system. This is a disadvantage. That is the reason why the lead compensators will create some attenuation at the starting stage itself. Lead compensator create some attenuation in the system to avoid that attenuation we use an amplifier such that hardware cost and complexity is increased, such that hardware cost and complexity is increased. Lead compensator creates some attenuation in the system. To avoid that attenuation, we use an amplifier such that a hardware cost and complexity is increased. Okay, now this is the advantages and this is the disadvantages of the lead compensator. Because of this attenuation, so the lead compensators are generally not preferred because of this attenuation. Okay, and you can easily identify here is also the noise can easily enter into the system here because bandwidth is more means noise power is also more. Okay, these are very, very important objective questions. Okay, note down all these things. Now this is a story of lead compensator, which is very important for an objective questions point of view. Now he is giving another compensator. Now he is saying that this compensator circuit will act as a lag compensator. You will verify, okay, how you are doing in the same. Now this is V0 of t, this is Vi of t, R1, C2, R2, and he says that this is the compensator. First we verify. Where verifying means we have to find the transfer function. Laplace transformation of V0 of t is V0 of s. Laplace transformation of Vi of t is Vi of s. R2 is R2, R1 is R1, C2 is 1 by SC2. Then you find the transfer function. What is the transfer function? Now the transfer function, Laplace transformation of output, voltage across this resistance R2 plus 1 by SC2 by the total resistance R1 plus R2 plus 1 by SC2 into the supply voltage Vi of s. What is the transfer function? Laplace transformation of output by Laplace transformation of input, which is equal to 1 plus SC2 R2 by 1 plus R1 plus R2 into SC2. Now the transfer function, this is the transfer function. Now in the denominator itself, I just multiplied with R2 and divided with R2. Okay, I just multiplied with R2 and divided with R2. So can I write like this? Now this is lag. So lag time constant. This is the lag time constant tau, which is equal to R2 C2. Now this is the lag compensator constant. This is the lag compensator constant alpha, which is R1 plus R2 by R2, which is alpha greater than 1, right? Now this is the lag compensator. Can I replace here? So what is the transfunction? Now V naught of S by Vi of S, which is equal to 1 plus tau S by 1 plus alpha tau S, where alpha is greater than 1 here, not less than, where tau is R2 C2. But now if you see the transfer function here, what is the transfer function? V naught of S by Vi of S, which is equal to 1 plus tau S by 1 plus alpha tau S. The lag compensator will not create any attenuation. Okay, see here. But in the lead compensator, it will create some attenuation. To compensate that attenuation, again we want to use some amplifier, and cost and complexity increases. But there is no extra hardware here. Okay, that is the advantage of this lag compensator. Now, what is the corner frequencies? Now this is the corner frequency omega c, which is equal to 1 by tau. This is the corner frequency which is equal to 1 by alpha tau. Now let us take for example tau equal to 1 second. Alpha is greater than 1, therefore let us assume alpha is some 10. So where is the 0 location? Minus 1 by tau means minus 1 by 1, which is minus 1. Where is the pole location? Minus 1 by alpha tau, minus 1 by alpha is 10 into 1, which is equal to minus 0.1. Now where is the pole zeros location in S plane? Where is the pole zeros in S plane of a lag compensator? Now this is the S plane. Now first one is pole, next one is 0. This is minus 1 by alpha tau. This is minus 1 by tau. This is the pole 0 sequence. First one is 0, next one is pole. What is the pole 0 sequence? Minus 0.1 pole, minus 1, 0. Now this is the pole 0 sequence of lag compensator, and what is the first one is pole, next one is 0. What is the pole 0 sequence of lead compensator? First one is 0, next one is pole. Now this is the pole 0 sequence of lag compensator, and this is the transfer function, and this is the compensator constant, compensator time constant. Now this is a no attenuation, nothing. Okay. And one more thing is also I am saying, while we want to draw the Bode plot, now write the corner frequencies in the ascending order. You know how to draw the corner frequencies in the ascending order. Okay, you just note down this.